have that.
I used to.
So
And
probably
I got
a lot of it very much into it. So.
maybe one day when I can have like the perfect nutrition.
Yeah, that way we can actually track everything.
Until then, just for looks. Yeah. Are you squatting often?
Yeah, because we do like weights like twice a week.
Oh, nice. Okay. What's that looking like? Thank you.
I did.
So there's assignment due today, right? And any issues on that? The assignment due today? What's the pressure level? 0 to 10?
100.
It's okay?
8.
I only see 4 people submitted. Maybe there will be more later at 11:59 p.m.
VLSI pressure level is 10.
Oh, really? For the labs?
Yeah.
Okay, yeah, I can tell. So I don't have any homework assignments. You know, it's just the quizzes and labs.
Yeah, that's fair.
So there's a new tutorial today to be introduced, and compared to the previous one, I think this is a little bit easier and shorter and easier. So I think it's reasonable to make it due Friday next week. Okay, so we can introduce another new tutorial on Friday. The IR transmission stuff, a lot of fun playing with that. And the week following that, we will start doing our PCB design. Okay, I'll send you some PCB design tutorials so you can follow this tutorial and start making our PCB, work on your own PCB. Okay. So PWM, if you look at the in class, right? So the first question here is, what is PWM? It's a pulse width modulation. If you look at the diagram over here, it's different from square waves, right? Usually the digital, we say it's a square wave. It's usually 50% duty cycle. It has 50% on and 50% off, right? But based on different applications, sometimes it requires the width of the pulse to be modulated. So the reason for that is to control the output power from the digital output. You know, all these microcontrollers, these are digital pins. If you are not using a DAC, if you are in VLSI, you have dealt with a DAC in lab 1, that's the ideal one. So the DAC is digital to analog converter. It receives the digital input from multiple pins and output one single analog output, right? So that's a DAC. However, if you don't have a DAC but you still want to output an analog signal to control different levels of voltages at the output, and you need a PWM. It's a digital output, but by controlling the output power, by modulating the width of the pulses, and you can mimic the analog output. So the applications of that could be an LED. So you can imagine if you connect one of the output pins, it doesn't matter, 10%, 25%, just one pin, right? One of the pins to the LED. Usually the frequency is at least several hundred hertz, right? It could be kilohertz. So it looks like it's blinking the LED, but since it's doing this really fast, you couldn't really see it. It's either being filtered out or you are not able to see the blinking of the LED at all, right? So eventually it outputs a different brightness at the LED. Another application could be the motor control, so the motor speed. So these could be real-time control, right? So based on the feedback, you can control the width of the pulses in real time. So if you hook this up to a oscilloscope, you can actually see that it's oscillating, right? Trying to adjust the output in real time. So that's a major way of controlling analog output in the industry, we don't really have other methods if you're not using a DAC, but DAC has other issues. Digital analog, if I drew the diagram over here, some of you haven't heard about that before. DAC is a digital to analog controller, right? So you have, for example, 8-bit of digital input is D7 to D0. And eventually there's an analog output, right? Analog output. So it's a D to A. But not all of the microcontrollers has a DAC. Like my Arduinos, I don't believe they have a DAC at all, right? So, but you still want to control analog, send out the analog output to control a sensor or something, right? So eventually you need the PWM to control it. Instead of using analog output, you want to use digital pulses, but control the width of it. All right, so motor control, LED, you can use it for temperature control, right? And also the PWM is being used for IR, infrared. Let me see if I posted. I haven't posted yet, but all the IRs are PWMs. Okay. Let's see. Now let's directly jump to the final demo video here and see what you're expecting.
So load the code to the board. It's right at 50% duty cycle, and now if I put a uppercase P,
and you can tell the LED is being
actually
controlled.
dimming it.
LED is the output.
Keep doing that.
So I'm
See it's being dimmed.
So what I'm doing is I'm typing a command into the serial monitor, and whenever the microcontroller receives that letter or command, it is able to reduce the duty cycle of the PWM, which is making it narrower, and eventually the output power will be decreased as well. So eventually it's dimming that LED. Right? And you can also enter a different letter to increase the duty cycle of the PWM or increase the width of the pulses, eventually to make it brighter. Okay, so that's how you control it through the serial monitor. That's from
and lowercase p will make it brighter.
All right, so this is given, this example here, okay? I'm gonna dive into this pretty soon. But now, the one you have to work on is it's called a color cube. It's a game. You can consider this as like a game. It's giving you effects on the light. So it's touring all the colors. You can choose a different path to tour. You can see the one thing you have to know is if you look at the schematic of the of the board. Basically, this is the night light for kids, right? I can imagine eventually. I think last year when I was in mines, some of the students made their own PCB and they were using an IR remote to control the light brightness. It's a really simple example, but they made their own PCBs. That's what I want you guys to work on as well. So something similar. You can see these are the RGB LEDs, right? So the three colors are being put into one component, one device, and there are actually three LEDs, three different colors in it, okay? And they are both shorted. So one quick question over here, right? So it's like a common sense, so if you guys know it. What is this code? What is the configuration code? Like connection. Have you heard about that before in circuit one? No? Okay, so if you see all the LEDs, so the LEDs are PN junctions, right? So they, whenever you forward biased it, forward bias means you have a higher voltage at the anode and lower voltage at the cathode. So the cathode has a bar here, right? And the anode is the other side of the triangle. So you can see the 5 volts is connected to the anode, right? Anode, and you are shorting all the anodes to one pin. And it's called common anode configuration. If you can also short all the cathodes to one pin, and that's called common cathode configuration. Because you only need to control one terminal of it in order to turn on off, right? So you don't have to leave both terminals open. You know what I mean? So it's just a short one side of all the LEDs to 5 volts for all of them, and it's just a toggle one side, just toggle the cathode over here. And one thing I want to let you know that you don't directly look at the LED if you give a it has 255, but actually it's a full brightness. That's just too bright, because you can if you look at the current limiting resistor, only 2.2 ohms. We should actually use a bigger resistor. It's making the LED super bright. I would recommend probably use the paper, like the US letter paper on the top of the LED when you are programming it. Okay, it's hurting your eyes. So in that case, if you want to turn on the LED, should you give a 1 or 0 to the pin here? You should give a 0, right? So if you give a 0, you'll turn it on. If you give a 1, you'll turn it off. Does that make sense? All right? Because if you give a 1, it's 5 volts, there's no voltage drop, so there won't be any current going through this LED. Right? Give a 1, turn it off. Give a 0, turn it on. So knowing that, you can see in this coordinate, right? So all the colors. If you, let's say it's 8-bit PWM, right? 8-bit PWM, which means the full range will be 255, and 0 will be totally 0. Slow it down, right? So we are talking about the duty cycle, right? So this is called the. So the length here, the ratio of the length here compared to the whole period, and that's called the duty cycle, and that's a percentage. Okay. For this one, it's pretty much 50% duty cycle. It's 50% duty cycle. And for example, the digital output allows us to give from 0 to 255. So you can definitely customize it, but now let's say it's an 8-bit for the counter, so it's from 0 to 255. So this has a full range. So in that case, 255 will give you a 5 volts, just continuously, just 1, right? Constant 1 over there. 0 will be just a 0. Okay, so if you look at this coordinate, I'm putting a 0 here at the red axis, which means if you give a 0 to red, and top means 255 in this example, right? So the reason I put a top at the origin is because when you give 255, you actually turn off the LED because of the connection like this, right? It's called the active 0 connection. It's active 0 connection. So give a 0, it's active. It will turn on the LEDs. So it's active 0 connection. So in that case, if we have 255 at the top, then for all the 3 channels, if I give all 255s, it's going to turn off all the LEDs. That's why top is being put in the origin, because it's going to turn off all the colors. Does that make sense? Okay. And then if I keep blue, green, both at 255, right? And I give 0 to the red channel, will show you just the red color. It's going to be the full brightness of the red, so it's going to be a red LED without any other colors. It's not mixed, right? It's just pure red and full brightness. Okay, same for these ones. If I give a 0 to green and top to blue and red, or 255 and 255 to red and blue, right? And 0 to green, I will turn on the green LED to the full brightness only, and all the other 2 will be turned off. So that's why if you look at this example here, right? So for red, remember it's always following the order of RGB. It's RGB. So in here, the 3 colors is 0, 255, 255. So it's gonna show red only. Okay? All these are different colors. Fuchsia, something. Turquoise. Yeah. Do you know what this color is? It's like a purple, sort of purple color. And this is I like this color a lot. Let me see if I can see a color of this color. I couldn't. But do you guys know? Probably your shirt, very close. Stevens. I'll just Google it for you. Right? It's turquoise.
We have done
Right.
this.
Where? Yeah.
And she has earrings.
Very close, yeah. So that is 255. So for turquoise, you have to mix G and B, right? So G and B are fully turned on, and red is totally off. So turquoise doesn't have any red component in there. For this fuchsia, I think it's a purple color. Let me search for that. Purplish. It's purple, right? Yeah. How to pronounce it? Fuchsia? Fuchsia? Yeah. So that is red and RGB. Red and blue, right? Red and blue mixed. Blue is just blue, green just green, yellow is red and green, right? So on and so forth, just let you guys know. So these are the code for all these colors, right? It provided to you guys, and so it's gonna tour the color from. It doesn't matter where it got started because it's touring all of them and coming back and just keep going all the time, right? So if, for example, if it starts from yellow, right? Start from yellow, and it has to follow this purple line. If you want to design a different path, which is fine, but you have to show that in your report, right? So show me like which path you are actually following, and then submit a demo video with it. Okay, but for this guy, you can see it's from yellow to red, right, and then to fuchsia, and then to blue, to turquoise, and then back to green, and then back to yellow. So the color, it's touring the color by using ISRs, because we want to use ISR to time it. Whenever the color is changing from, for example, from let's look at the code here, right? From this guy, from red to fuchsia, from like this line here. Whenever it gets into ISR, it changes the values of PWM with a certain step size, right? The step size could be a value it's adding or decreasing from the 255 over here. You know, if for example from red to fuchsia, right? If you compare every single channel, so the red channel is not changing because it's always 0, and the green channel is not changing as well. So the only thing that's changing is actually the blue channel. So if you want to tour the color from red to fuchsia, so the blue color is the only one that is changing. So it's just every time it enters the ISR, you decrease that blue channel's value by a certain number, and that will be called the step size or the step number, right? It could be 2, could be 1, doesn't matter. But you design your ISR with a certain timing, right? So every time it enters, it decreases. So if you play it, you can see it's actually changing the color from red to fuchsia smoothly instead of just directly changing from one to another, right? And that is why eventually you are able to see a effect.
All right, so this is a demo for the color cube experiment. You can see I have 3 jumping wires, and they are shorted to the RG and B LEDs. But the thing is, I don't have enough number of female to female connectors. That's
Again, so I have the female to female connectors for you guys, but I didn't bring that home. That's why I didn't use it. But eventually, it's just the female to female connectors. You don't really need a breadboard. Okay.
so I'm using a breadboard in the middle as a connector to do a female to male and male to female connections. So, but the thing you need to know that is it's A76. Okay, it's A76 is the pin numbers, and they are shorted to R, G, and B in a certain order. Okay, you can see from the pin headers over here, the bottom one is red,
Yeah.
and G and B following that certain sequence. So after the connection is made, come to this serial monitor and do a uppercase C, enter. It will start twirling all the colors from the color cube. Okay, make sure it tours all these colors defined in the tutorial. Okay, and then lowercase c will stop it. It's gonna stop at a certain color, and then lowercase a will just turn off the LED. Right, and then you can use I think it says lowercase z to clear up the monitor. And you should be able to restart the color tour by putting an uppercase C over there. It comes back. Okay.
Okay, so that's the final result. How to do it? Okay. Now let's look at the in class. So the PWM has several different modes, right? So the one we are using for the task 1 here is called the fast PWM mode. It could be a little bit confusing, but it's just a certain pattern. If you remember it, understand it, it's actually really simple. And you can see there are so many different modes, okay? And the one we will use for this one, in the example for task 1, and the one for the IR transmission example next week, it's going to be mode 14. Keep that in mind. Mode 14 is the one we are going to use here. Okay, and interestingly, so this mode, we're going to make the color cube a little bit, easier. So we are not using the mode 14 for the color cube. However, it's being used for the first example, which is given over here, okay? But it's going to be used for the first one here in this tutorial, and also the IR transmission example next week. But the color cube one is a little bit easier. I'll show you pretty quick. So now, for this one, what is this doing actually is, if you look at this diagram, it shows the concept over here. So the counter, for example, we choose a pin number as the output. Okay, so the PWM pins, not every single digital pin can do PWM. Only certain pins can do PWM. And they are all named as OC something something. So it's OCnx. N means 1, 2, 3, 4, 5, right? X means A, B, or C. So if you see OC, it's output compare or something. OCnx, that's going to be a PWM output pin. And this number here is controlled by which timer or counter. If you see OC2A, that's OC timer 2 controls this PWM. And it's the A of that PWM module. You can see everything. Usually they have A, B, and C. For example, this guy, okay? OC4A, OC4B, OC4C. So these are the PWM output pins that controlled by timer counter 4 and ABC modules. Does that make sense? This can be really confusing because you can see a lot of keywords are very similar to each other. So that's OCnx, right? OCnx. And there's another one, it's called OCRnx. OCRnx. The R means the register. So that one controls the timers. It's a comparison. So the register stores a value in there, and the timer is going to count until that point and then do something. It could be pulling that down to 0, or it could put up to 1, depending on the different mode you're using. Okay? So it's OCRnx. But the pin is just OCnx. So OCRnx, that's the register. It's not a pin, it's a register. For mode 14, this diagram shows you the mode 14 of the PWM module used for using timer and counter 1. Okay? See OC1A, that's the pin. Alright, that's the pin, that's the output pin. OC1A. Okay? And that's a waveform shows up at the pin. So for mode 14, if you look at duty cycle, if you look at the PWMs, there are two parameters you need to control, so you can determine the feature of the property of the PWM. So first is the frequency, right? This is the frequency. Second is duty cycle. So if you know the frequency and the duty cycle, you know exactly what the PWM looks like. Does that make sense? Right? It could be the frequency of it. It could be this, right? First, you need to know the frequency. Second, you need to know the duty cycle. So when you are designing that your PWM output, right, for mode 14, this count over here, ICR1, which is the register, that defines the top. So you will see this keyword a lot. Top, right? So top and bottom. So bottom is usually just 0. So bottom is 0. But top is the top that the counter will count up to, and then will clear the counter, and also the TOV flag, and restart from the bottom for the counting. So for mode 14, the top is defined by this register, the value being put in this register, which is ICR1. So that's another register you need to know. So when you are doing the setup, you put all the configurations of the PWM in the setup function. You need to give, first you need to set it for mode 14, right? So mode 14. And for mode 14, that needs two parameters. The first one is ICR1. It's a register. You need to put a value in there, and that defines the count. So it counts up to that number, and then it's going to start counting from 0. So that defines the period. You can see here, right? So that's the output of the PWM. This count actually defines the period from here to here. That's the period of the PWM output. And OCR1A or OCRnx, right? So that's the general term of that. But for this case, we are using timer 1A module. So OCR1A, that register, stores the value for this count. Just basically defines the duty cycle. Too much? No? Is that okay? Doable? So one quick question. So given that you know what is being put in OCR1A and you know what is being put in ICR1, do you know the duty cycle of it? How to calculate it?
ICR1 is like the frequency, and then OCR1A is the duty cycle count.
Yeah, so it's basically OCR1A divided by ICR1. Right? These are just different counts. So for example, the counter started counting from 0, okay? It starts counting. It counts up to OCR1A, it pulls it down. Alright? And then keep counting, counts up to ICR1, it pulls it up. And then it starts counting from 0 again. So basically, ICR1 is the number of counts that defines the period, the whole period. And OCR1A defines when you want to put down, so you can have that little on time, right? You define when on time ends. So to make it simple, very simple, okay? A PWM, you know that you need to know the period of it, right? And also you need to know the on time of it. So you know the duty cycle, you know the frequency. Does that make sense? So what defines the frequency? OCR1A. What defines the duty cycle? OCR1A. And what defines the frequency? ICR1. All right, pretty simple, just two parameters, really simple, right? So when you're programming, depending on the application, first you need to define the frequency, right? So the frequency, ICR1. And then you want to just directly give a certain duty cycle, like 10%, for example, that's a pretty normal duty cycle for IR transmission. You just directly assign ICR1 divided by 10, right? And assign it back to OCR1A, and then you're done. Okay?
So for this, would you give TCNT1 account of OCR1A? And
No,
then once
it's-
it overflows, do something and give it account of ICR1 minus OCR1A?
No, it always comes from 0. You can definitely put a starting value in the counter 1, but it's just complicating things, right? Since you already have the two values to control the duty cycle and frequency, why do you have to change the counter though? I mean,
So
the
how does
counter.
it know to like how does it know when you hit OCR1A?
When it hits, it directly pull it down. It's a digital circuit design inside.
Oh, okay.
Yeah,
Okay.
yeah. So there is a flag. The name is like TOV, I think. Let's take a look. So you are not manually toggling this guy. Doesn't like the speaker. You are doing the
Right.
digital right. No, it's
Okay.
it directly pulls it down, and that shows up as this pin.
Gotcha.
Yeah. So that's why you want to directly throw a number in here, and it will directly do it for you.
Cool.
Okay. And there will be a flag being turned on, so you can have an indicator. Sometimes you may need it. I don't know. But so whenever this is getting, what is it called? It's an output compare register, right? So comparing with the counter's count. So when the counter is counting, it's comparing with this value here. It's output compare a register. Whenever the match, it's gonna pull it down by itself, and also there's a flag will be set, and I think that's TOV. Let's take a look. For this mode 14, right? Mode 14, you can see top is ICRn, right? ICRn, which makes sense because top is ICRn, like we just explained over here. Here's the top, okay, for mode 14. And update of this at bottom. I don't know what that means. And TOV flag set on. So there's the TOV being set at the top. So it's actually not when it matches. Whenever it reaches top, this flag is on, right? So it's basically that makes sense because that's a timer when timer overflows. So the top defines. So the top is not actually 2 to the 16th anymore. It's just reducing that top to a certain value you can define, you can customize. And then whenever it reaches ICRn, it's gonna turn on the flag, TOV. So turn on TOV, right? Timer overflows. Even though it's not reaching 2 to the 16th yet. But whenever it reaches this guy, it's already defined as a top. Okay? Let's come back to the in class, right? Where we are right now. Okay, another one. This is a advanced level of using PWM. However, there's a very regular way of doing that. You can see if you search online, you can see a lot of examples. It uses a function called analog write and the pin number here, and then it's giving a value from 0 to 255, whatever value in between this range, right? So 255 is going to give you a logic 1, and 0 is going to give you a logic 0, but anyone in between, it will give you a certain duty cycle of PWM output. So that duty cycle, if you give a 10, for example, that will be 10 over 255 of duty cycle, okay? So you can easily just use this function to output a PWM to a certain pin. However, compared to this method, what are the pros and cons compared to whatever we can do over here. You are just sending a PWM with a certain duty cycle to the pin. Right? What other things you cannot change over here? Frequency, right? So sometimes you need to define the frequency, which means yes, it's look at the same duty cycle, but the frequency is different. This cannot define the frequency. So if you directly use this one, the frequency is usually 480 hertz or 960 hertz. I think. Let's take a look. Oh, actually 490 hertz or 980 hertz, depending on which pin you are using, which PWM module you are using. It's usually 490 hertz or 980 hertz. So you cannot customize it. Okay, so to set it up to the mode 14, what are the registers that you need to configure? Mode 14, take a look. So to make mode 14 happen, WGM N3, N is the timer's number, and these are the bit locations. So we need a 1110, right? 1110 for these four pins, the WGM bits. 1110, okay, 110. So in that case, the code for WGM N3 to WGM N0 should be 110. And that number is basically just 14 in decimal, right? So 110 is 14 in decimal. So in this mode, as we just explained, by using this diagram over here, so which one defines the top, which one, so what defines the top and what defines the bottom? Top is what? ICRn, right? Bottom is 0. And which value determines the duty value? So we talk about the duty cycles. The duty cycle is the percentage, right? That's a duty cycle. And duty value could be the value of the counts of the on time, defines the on time. Okay, that's the duty value. So which number which register or what value determines the duty value? OCRnx, right? Because OCR1A is the module for timer 1, counter 1, and the module A. However, in general, it should be OCRnx. OCRnx. Now let's come back to this table. These are another 2 bits to control the, like when you want to flip it or set it, right? So there are 4 different modes. 00 for these 2 bits are just basically not doing any PWM output. And for 10 is the one we are going to use, right? But for, if you look at number 6, question number 6, so let's set these 2 bits to be 10, okay? To be 10. Which pin, all right, the pin name and pin number, you need to put a pin name and pin number in there, will be set when will be set during when, right? And it will be cleared during when. Is that confusing? So take a look at this one. So this mode, okay? You see, it's gonna clear OCNA. What is that? OCNA, OCnx, right? OCnx. What is that? Clear that on compare match. So what are these? PWM outputs. These are pins, right? Physical pins. OCnx pins. So it's gonna clear that pin on compare and match. clear it on compare match. Compare match to what? Whenever it matches what? Keep in mind, compare match is only for that OCRnx register. Okay? So it clears it here, and then it says it's gonna set that pin at bottom, which is whenever it's done with the counting, right? It will directly come back to bottom, which is 0, and start counting from 0 again. And this mode is called non-inverting mode. It's giving you more names. Non-inverting mode, doesn't matter, it's just called non-inverting mode. So inverting mode, it's just inverted compared to this one. So can you tell me that? So see here, it clears that pin on compare match and set it at bottom. So if you look at this one, is this non-inverting or inverting? So clears that pin at compare match and set it at bottom. That's non-inverting. Is this non-inverting or inverting? The first one, right? It's non-inverting because it clears it at the compare match, and then at the bottom, even though it's at the top, but actually it's whenever it's reaching the top, it's actually will directly come back to the bottom. So these two overlaps, right? So this one overlaps with the bottom. It sets at the bottom because this will come back to bottom. All right. So in that case, for question number 6, right? If I set COM 2A1, COM 2A0 to 10, which pin? Which pin is being controlled by this guy? Which
OC2A?
OC2A. If you look at OC2A, what's the pin number of it? Huh?
10.
Yeah. Pin 10, right? So digital pin 10. So Kai, when Kai designed the board, he labeled all the pin numbers. So these are the pin numbers you want to look at. So that's the pin 10. So when you are trying to use that PWM output from the board to control something, you can find out that pin number and connect it to your LED. So pin 10 will be used for that case. So pin 10 will be set when at the bottom, right? At the bottom. And it will be cleared. When it matches what? When the counter matches what? So that pin 10 will be cleared when it matches, when the counter matches what?
OCR2A?
OCR2A, yeah. OCR2A. Okay? I have to make it every single one right. It's not OCR2B, it's OCR2A. If you would like to use the B modules, you need to come back and configure the B modules instead of the A modules. Okay, so for the registers for here, the B modules need to be configured instead of the A modules. How? These are all just the physical bits in the registers. If you look at the TCCR1A, which is the one we have been using a lot, but we never accessed, we have never used these bits in the past, but now is the time, right? TCCR1A, you can see it has all the COM NA pins and NB pins as well, and C's as well. So depending on which one you want to set or reset, you just directly configure it using the Arduino code we have used it before. That answers question number 7. Question number 8. Write an Arduino code snippet to configure these 4 bits to be 1110. How to do that? So first you have to find out which register has which bits, right? This is really interesting. TCCR1A has WGM11, WGM10, and TCCR1B has WGM13 WGM12. So I have to do that separately. I do that separately. And you can do two at the same time. Remember? You can do two at the same time. I'll show you. I'm not showing TCR1A, right? So TCC, that's what you have to figure out by yourself. And for TCCR1B, right, you have this, and you can do this. 2 bits at the same time. Because for 1110, right, so 1110, so you have 3, 2, 1 to be ones and 0 to be 0, right? So 0 don't have to touch it. You just have to do OR logic for these 3 bits. So you need these 3 bits and 1 and shifted by these 3 bits, right? And for these registers and do OR logic. Number 9. Write a setup configuration, function configuration code snippet to use OC3B as a PWM output at 40 kHz, 10% PWM waveform under mode 14. It's a timer scaler 1-to-1. So the calculation has to follow this equation. Where is it? Jesus, where is it?
For things like this on the midterm, will we have the registers, these
Yeah.
charts of the registers to look at?
Yeah, I'll have it. I'll make it reasonable. I haven't made up the midterm yet, but I'll make it reasonable. Yeah.
So we don't have
If-
to memorize that
Yeah, remember something, but not everything. Definitely. Yeah. OCRnx. Alright, so that's the frequency of it. Okay? So that's the equation you want to use. I already divided by 2? I don't think it's divided by 2. The waveform frequency is defined by the following equation. I got a 2 there. Why is 2? Oh, that's a different mode. That's a different mode. I'm sorry. So the mode we are going to use is going to be different from the one I saw last time. I don't know. I don't think there's a 2 there. I will fix that later. Okay, let's assume there's no 2 here for the fast PWM mode, because here it didn't give you an equation for this mode. It's just letting you know this guy. No, that's not right. So let's follow this one, but not without the 2 here. Okay, so follow this one with the 2 here. So the frequency, let me just write it down. So the frequency of the PWM equals 16 mega divided by the prescaler, right? The prescalers, and then 1 plus ICRnx, right? RCRnx. There's no X, just N. So in that case, if we want this to be 40K, right, and this is given that this is 1-to-1 prescaler, so there's no N here, I can easily calculate this guy, right?
What's after the 16?
16 mega. So that's the register you want to assign to. And if you're looking at the problem, it's module 3, it's timer 3. So eventually, this is ICR3, right? ICR3. So that's the register, ICR3. You need to give that value, ICR3, to that register. So the name of the register in the code should be just directly ICR3. So you need this line over there, ICR3 equals whatever you calculated over here, right? And then you set up all the other registers. And make sure you are doing it with the module B, right? The B module. So that's gonna be, we won't be able to finish that today, so we'll turn it in on Wednesday. So you can see that we are expecting it's com and B, com and B0, B1, B0 is 1, 0, right? So these two bits have to be, so this bit has to be set, right? And then you have 1110 here. 110 is giving you WGM 320 to be 11014, right? So these three bits need to be set as well. And at the same time, you need to turn on the timer. The timer. So the timer is also the prescaler. Turn on the timer is basically just to turn on the prescaler, set up the prescaler, as we all know already, right? So these three, if it's a no prescaler, then this bit need to be set, and that's that. These three bits belong to the TCR1B as well, so you can set up this, and this at the same time for this register. And for this register, you need to set this. So just two, right? 1, 2. And that need to be TCCR3A and TCR3B, right? So after you assigned this guy and 10%, it's just basically OCR3B need to be 10% of that number. And that's it. We'll finish the following two questions on Wednesday, okay?